5.3 Polynomial Functions. So we've been working with functions for quite a while now, and in particular we've worked with linear functions and quadratic functions. As it turns out, both linear and quadratic functions are a specific type of polynomial function. So remember, linear functions typically had x to the 1 power, whereas a quadratic function had an x squared. But what if I have an x cubed to the 4th to the 74th power? Well, those are still actually polynomials. So for our first definition, a polynomial function is a function that has this given form here: a sub n x to n plus a sub n minus 1 x to n minus 1 plus so on and so on. In other words, a polynomial is where I have coefficients and x to a positive power. For example, I could say I'm working with 3x to the 3rd power plus x to the 1 power plus 8. What I have here is a polynomial where my coefficients are non-zero and n is a positive whole number. Well, if I look at my highest power, or the highest exponent, whatever coefficient, the an, we call that the leading coefficient, and the highest power, or exponent, we call it the degree of my polynomial. So for example, here I have three functions. The first one, x to the negative 2nd power minus 3, this is not a polynomial. Polynomials cannot have a negative power. Here I have a power of negative 2. So that cannot be a polynomial. For my second one, this is a polynomial. I have 2x cubed minus 2x squared plus 3. In particular, this is a polynomial of degree 3. Note here that 3 is my highest power. And the leading coefficient is a 2. And for the last one, this one looks a little bit different. This is still a polynomial because I can rewrite it to match my polynomial form. It's actually just factored. Despite the fact that it's factored, we can still determine the degree of the polynomial and the leading coefficient. So this is a polynomial of degree 4. The reason that I know this is that from this first term, I have x to the 1 power. From this second term, if I were to multiply all of this out, I would end up with x cubed plus some other stuff here and there. So if I multiply an x to the 1 power and an x to the 3rd, I would end up with x to the 4th plus some other things. Again, for my degree, I'm only looking at the highest powered after it's in the polynomial form. And if you're curious, the leading coefficient of this one will end up being 1 as well. So what are we doing with a polynomial function? Well, we know one thing we're interested in is solving equations. So if I have some number k and I plug it into my function and get 0, in other words, when f of k is 0, you plug in a number into your function, you get 0 as your output, then we say that k is a 0 of my polynomial. Or you might say k is a solution to my polynomial, depending on the book you're using. Well, furthermore, this also gives us a very important idea. This tells me that if I were to factor my polynomial, then x minus k is a factor of my polynomial. So for example, if I have the polynomial x squared plus, let's do plus x minus 6 equal to 0. We know how to solve this polynomial. We can do quadratic formula, we can solve through factoring. We have multiple ways that we can deal with this. We know if I factored, I would have x minus 2, x minus 3 equal to 0, which tells me that x is equal to 2 and x is equal to 3. Oops, sorry, I said minus 3. I meant plus 3, giving me negative 3. All right, so noticing here, my two solutions for this polynomial, this quadratic in particular, is 2 and negative 3. Hence, I know if I were to factor this polynomial, it should factor down into, well, x minus 2 and an x minus negative 3, or in other words, x plus 3. All right, so this is really good for whenever I have a set of separate zeros. But what if I have x minus k to the m power is a factor of my polynomial, but x minus k to the m plus 1 is not? Then we say k is 0 with multiplicity m. What does this mean, informally speaking? So let's look at this example that I have in the definition. If I have f of x is equal to x squared times x minus 1 cubed times x plus 2 to the 5th power, I first can figure out what my zeros or solutions are. In other words, if I had set this equal to 0, you could tell me that x is equal to 0, x is equal to 1, and x is equal to negative 2. because we can set each term equal to 0. Well, now that I have 3 zeros, I may ask what's the multiplicity of each 0. So for x equal to 0, I notice that I got this from x squared. Well, this tells me that 0 is a 0 with multiplicity 2. If I look at x equal to 1, I get this from x minus 1 cubed equal to 0. This had a cubed, so 1 is a 0 with multiplicity 3. And then for my last 0, x is equal to negative 2, I got that from x plus 2 to the 5th power being equal to 0. This tells me that negative 2 is a 0 with multiplicity 5. So why do we care about multiplicity? Well, as it turns out, if I know what the multiplicity is, it gives me some valuable information about the graph of the polynomial. If a 0 has even multiplicity, then I know that my graph only touches the x-axis at that 0. However, if we have an odd multiplicity, then the graph crosses the x-axis at that 0. So, in other words, if I were to draw some random graph, and then I drew my curve, all of the points that hit the x-axis, these are my zeros. Well, if I have an odd multiplicity, then it must be that my graph passes through the x-axis. In other words, I have something like this right here. What I've circled with this pink highlighter, this means that my 0 has odd multiplicity. Whereas if I square this other one, put it in a square, not actually squaring it, this 0 only touches my x-axis, so that tells me that here I have an even multiplicity. So the first one was an odd multiplicity, the second one was an even multiplicity. So this is our idea of zeros and multiplicity. Well, now that we've talked about the zeros of a polynomial, let's go ahead and talk about some end behavior. Whenever I'm discussing end behavior of a polynomial, I mean on the far left and the far right. Where is my polynomial graph heading towards? As it turns out, depending on the degree of the polynomial and the leading coefficient, I can figure out what the left end behavior and the right end behavior is. So take a moment to pause and read through this table that I have here. So you may be thinking that this is a lot to remember, but we actually have been working with this before. For example, if I have a quadratic function, let's say f of x is equal to x squared, we know what an x squared graph looks like. If I were to graph it, then I would end up with something that looks like a parabola opening upwards. So looking at this function x squared, this is an even function, or even degree, sorry, an even polynomial, and the leading coefficient is positive. So based off this table, if I have an even polynomial, and the leading coefficient is positive, on the left, I should be going up towards infinity, and on the right, I should be going up towards infinity. And that's exactly what's happening. If I look on the left, I'm going up towards infinity. On the right, I'm also going up towards infinity. So we're now going to use our information about multiplicity and the end behavior of a polynomial to give a rough sketch of a factorable polynomial. So let's go ahead and look at example 1. Consider f of x is equal to negative x squared times x minus 1 times x minus 5. So for part A, list all real zeros and their multiplicity. So for part A, to figure out the values of my zeros, I'm taking my function and then setting it equal to 0. That's actually where we're getting find the zeros from. So I'm setting it equal to 0. And since it's already factored, just like a quadratic, I can set each individual term equal to 0. That is, I can get negative x squared is equal to 0, x minus 1 is equal to 0, and x minus 5 is equal to 0. So if I solve for x on each one, on the left, we can pretty quickly see that we get x is equal to 0. In the middle, if I add 1 to the left and the right, I get x is equal to positive 1. And on the far right, if I add 5, I get x is equal to positive 5. So I have my 3 zeros. But what's their multiplicity? Well, to figure out their multiplicity, I just have to look at, from the factor that they came from, what was the power of that factor. So for part A, sorry, not part A, x equal to 0, the first 0, I had x squared. This tells me that my multiplicity was 2. For x equal to 1, I just had x minus 1 to the 1 power, telling me I have multiplicity 1. And for x equal to 5, x minus 5 was a power of 1, telling me I had a multiplicity of 1. One thing that I want to clarify, whenever I say the power of 1, I'm not referring to the power of the x's, but rather the power of the factors. So my powers, or my multiplicity that I was referring to, was from the factor, not from the x itself. So we have part A. We have their zeros and their multiplicity. Now for part B, for each zero, so I have 3 of them, determine if they touch or cross the x-axis. So remember what I said earlier in our definition. If we have an even multiplicity, we only touch the x-axis. If my multiplicity is odd, then we cross the x-axis. So for x equal to 0, we have multiplicity 2. Clearly 2 is even, hence we only touch the x-axis. For x equal to 1 and x equal to 5, we have an odd multiplicity, so we cross the x-axis. And this is what I want for part B. For part C, I want the leading coefficient, and I want the degree. So, for my leading coefficient, it may look a little bit odd right now, but I want you to imagine if I did multiply all of this out, my entire function, what would be the highest ordered term and what would be my degree? In this case, it might be easier to think about the degree first. From my first term, negative x squared, I have 2 for my adding 2 to my degree. For the x minus 1, that adds 1 to my degree. And x minus 5, that adds another 1 to my degree. And hence, I know if I were to multiply out this function, simplify it as needed, then my highest power would come from an x to the 4th power. That is, my degree is 4. Another way that I could have thought of this is that my degree is simply thought of as the sum of my multiplicities. Remember, my multiplicities here are 2, 1, and 1. This tells me my degree should be 2 plus 1 plus 1, or 4. So that covers my degree. What about the leading coefficient? Again, if I look at this function, I want you to imagine if you multiplied it out. What would go in front of that x to the 4th? Well, if you think about it, our x to the 4th will come from negative x squared times x times another x. So in particular, I know that if I were to multiply this out, I would end up with a negative x to the 4th. In other words, my coefficient, I'm expecting it to be a negative 1. So I have my leading coefficient and the degree. Now for part D, I want to ask for the end behavior. Remember, for end behavior, I had to check, am I an even degree or odd degree? And is my leading coefficient positive or negative? Well, since my leading coefficient is negative and my degree is even, I simply have to look at my table for even degree, negative coefficient. So if I have an even degree and a negative coefficient, leading coefficient in particular, then I know on the left, I start going to negative infinity, and I end going towards negative infinity. That is, I'm expecting the far left and the far right of my polynomial to be going down to negative infinity. So we know on the left, I'm going to negative infinity. On the right, I'm also going to negative infinity. So now I have everything I need to figure out what my graph may look like. So, looking at this Cartesian plane, part E, roughly sketch my graph. I'm going to use each step of my problem as needed. First off, I know I have a 0 at x equal to 0, 1, and 5. That is, I touch my x-axis, or cross it, at 0, 1, and 5. I'm not being completely exact here. I'm marking my 3 points, x equal to 0, 1, and 5. Then I know for my end behavior, on the far left, I should be at negative infinity. So let me put a mark down here at the bottom on the left. And I know I want to end at negative infinity. So I'm putting an x there for now, just to show and remind myself This is where I want to start and end. All right, so starting on the far left, if I draw my graph coming, then I know that at x equal to 0, I have multiplicity 2, or in other words, I should only touch my graph, or touch my x-axis. So I'm going to draw this graph as if it was touching my point x equal to 0. And then it continues, and I know eventually I have to return to x equal to 1. In particular, we know that my graph touches x equal to 1, and it crosses. So again, I'm doing a very rough sketch here. And then for my last one, eventually I had to hit x equal to 5 as my 0. And I know that my graph at x equal to 5 crosses the x-axis. So I have a very rough sketch. If I were to clean it up a little bit, I could make it a little bit nicer. I'll draw it with a slightly different color. If I were to draw it a bit nicer, it might look something more along the lines of what I have here, more or less. But more importantly, I know on the left and right, I'm going towards negative infinity, meaning I'm going down. I touched the x-axis at x equal to 0, and I cross at x equal to 1 and 5. This is roughly what my graph may look like. So we have example 1. Now for example 2, consider this function 3 times x minus 7 times x plus 3 squared. Same instructions. So we're going to go down our list. For part A, I want all the zeros. I can do that by setting my function 3 times x minus 7 times x plus 3 equal to 0. So from here, I can set each term equal to 0. 3, I don't have to worry about my coefficient of 3 in the front. That's not going to give me a 0. I just have x minus 7 is equal to 0. X plus 3 is equal to 0. So if I solve for x each time, I get x is equal to 7. And x is equal to negative 3. So I have 2 of my zeros. What's their multiplicity? For their multiplicity, for x equal to 7, again, I return to the x minus 7, and I look at what was the power of this factor. Well, the power of this factor was just x minus 7 to the 1 power. So I have a multiplicity of 1. What about for x equal to negative 3? Well, if I look at x plus 3, the factor from which it came from, it was x plus 3 squared. So hence, I have a multiplicity of 2 here. So I have 2 zeros in each of their individual multiplicities. Now, I want to determine if they touch or cross the x-axis. Well, this is quite simply if they touch, if my 0 touches the x-axis, then I should have even multiplicity. If it crosses, we have an odd multiplicity. So, for x equal to 7, my multiplicity is odd, so I know I cross the x-axis. And for x equal to negative 3, I touch the x-axis, because we have an even multiplicity. Continuing from here, let's do part C. Part C says, what about the degree and the leading coefficient? Remember, the degree tells me if I'm an even or odd degree. And then my coefficient combined with my degree tells me my end behavior. So I'm just abbreviating lead coefficient here to save some time. So starting off with the degree, we can think of this several ways. If I look at my original function, I can think, if I multiply this out, what would be the highest power? Or we can simply add our multiplicities together. In either case, I should end up with a degree of 3. For the leading coefficient, I can imagine if I take 3 times x squared, I would end up with 3x cubed plus some other material. In other words, I'm claiming my leading coefficient is also a 3. You can verify this again by, if you want to, you can multiply out this entire function. You will get 3x cubed plus some other stuff. Now we can move on to part D, the end behavior. Well, I must refer back to my table and what my degree and leading coefficients are. My degree is 3, which tells me that I have an odd degree. My leading coefficient is also 3, but for leading coefficient, we're worried about if it's positive or negative. In this case, my leading coefficient is positive. So, referring back to my table, odd degree positive leading coefficient. So we have an odd degree. And then we said our leading coefficient was positive. So I must have this type of end behavior. My left end behavior goes to negative infinity, whereas my right end behavior goes to positive infinity. So let me go ahead and write that down. On the left, I said that we go to negative infinity. On the right, we go to positive infinity. In other words, on the left, I'm starting on the bottom, and then at the far right, I know I should be ending up on the top, going upwards. So now let's go to our graph sketch. If I go to my graph sketch, just like before, I like to note with an X that on the left, I started on the bottom, and by the time I'm on the far right, I should be ending up going upwards towards infinity. Next, let's go ahead and map out our multiplicities, our zeros. For our zeros, we have a zero of -3 and 7. So on my x-axis, I'm going to put x equal to -3, roughly give or take, and x equal to 7. Again, I'm not being completely exact here, but we're just looking for a rough sketch of the graph. All right, so now I go ahead and I like to start on the bottom left. In this case, the bottom left. And then I go towards my graph, my zero. Well, at x equal to -3, I had an even multiplicity, so I know I must be touching that point, not crossing my x-axis. I continue forth, and I know I must touch my second zero. And for x equal to 7, I should be passing through the x-axis. Well, this is great because now, without even thinking about my end multiplicity, it completely matches. I started on the bottom on the left, and I ended up on the top for the right side. So this is my rough sketch of this function. If you put this into your graphing calculator or into a graphing software, you'll see we'll get something that vaguely resembles this. We don't know how far down to go, but we're just looking for a rough sketch. And so that completes our example 2 and the last example.